Corona discharge is a high-voltage phenomenon in which an intense electric field around a conductor ionizes the surrounding air or gas, resulting in a faint bluish-violet glow and a hissing or crackling sound. This effect occurs when the electric field near the conductor accelerates free electrons to high speeds, causing them to collide with neutral air molecules and strip away electrons. As more molecules are ionized, a cloud of ions and electrons forms, creating a conductive path for current flow. Although the discharge current is small, its effects can be significant, particularly in high-voltage environments. Corona discharge commonly appears around high-voltage equipment, such as power lines and transformers, especially at sharp points or edges, where the electric field is more concentrated. It is often visible in low-light conditions, like in dimly lit substations or on power lines at night, due to the faint glow produced by ionization. The ionization process underlying corona discharge begins when the electric field reaches a critical threshold, typically a few kilovolts per centimeter, which provides sufficient energy to free electrons from air molecules. These free electrons accelerate under the electric field, colliding with other neutral molecules, creating a cascading ionization effect. The ionized air acts as a partial conductor, allowing current to flow between the conductor and its surroundings. Corona discharge can be either positive or negative, depending on the polarity of the conductor. In a positive corona, the conductor is positively charged, attracting electrons from the surrounding air. This form of discharge is steadier and less intense, resulting in a milder glow and quieter effect. Negative corona occurs when the conductor is negatively charged, causing free electrons to accelerate away from the conductor. This form is generally louder, more intense, and can be more damaging to materials. The occurrence and intensity of corona discharge depend on factors such as conductor shape, environmental conditions, and voltage levels. Sharp edges or pointed shapes concentrate the electric field, making corona discharge more likely. Higher humidity can dampen ionization by introducing water vapor that absorbs energy, while lower air pressure at high altitudes reduces the air's dielectric breakdown threshold, making corona discharge easier to initiate. High voltages also amplify the electric field, increasing the chance of corona. Despite its challenges, corona discharge has practical applications in several fields. For example, in ozone generation, it converts oxygen molecules into ozone, which is a strong oxidizer used in water treatment, air purification, and sterilization. In air pollution control, corona discharge is utilized in electrostatic precipitators to ionize dust particles, enabling them to adhere to charged collection plates for efficient removal from exhaust gases. It is also used to treat non-conductive surfaces, such as plastic films, to improve their adhesive properties for printing, painting, or coating. In copiers and laser printers, corona discharge charges the photoconductive drum, enabling toner transfer to paper for image creation. However, corona discharge can be problematic, especially in power systems. It can cause energy losses in long-distance transmission lines, where the small current from corona effects, though minor, can add up across vast grids, reducing efficiency. The ionization process produces electromagnetic interference, EMI, that can affect nearby electronics and communication systems, especially in sensitive areas. Corona discharge also degrades insulating materials as ions bombard the surface, causing microscopic damage that accumulates over time. Additionally, it produces reactive chemicals like ozone and nitric oxide, which can corrode nearby materials, especially metals, creating more maintenance requirements. To manage corona discharge, engineers use several design strategies. Rounded conductor shapes are preferred over sharp edges, as this helps spread the electric field more evenly and reduces ionization. Corona rings, or grating rings, are often installed around high-voltage conductors to evenly distribute the electric field, particularly in substations and transformers. Increasing insulation thickness and spacing between conductors can help keep the electric field below the ionization threshold. In controlled environments, adjusting humidity and air quality can also help reduce corona discharge, especially in high-voltage labs or industrial spaces. Corona discharge is a complex phenomenon with advantages and drawbacks. It plays an essential role in applications like water treatment, air purification, and material processing, while also presenting challenges in high-voltage systems. Effective control and understanding of corona discharge are crucial to harnessing its benefits while managing its potential risks in power and industrial settings.